Howdy everyone, and welcome back. We've been talking a bit about optics. We've been talking about reflection. We've been talking about refraction, or Snell's law, and we're going to just continue with that idea by talking about it in the context of other things like lenses and mirrors. But it's really, comes from the same stuff. Mirrors going to create images because they reflect light, and lenses because they refract it, like we've been talking about before. But again, applying it to more practical things where we use that more. And so that when we talk about mirrors, in this case, they're going to be curved mirrors. So we're going to talk about them as being either concave, so the reflective points are inside, so it looks like a cave, it's kind of enveloping you, or convex, where it's going the opposite side, so it's like a bulging out mirror where the reflective stuff is all on the side and creating images. And then for lenses, convex lenses are ones that look like this, kind of like the stereotypical lens for glasses, and then you have concave lenses. But the point is, we're going to be using that. You're using the same stuff we just learned and using it in the context of other things that, more practical things. So let's learn some basics about how mirrors and lenses work and some mathematical things we do to find where the images that they create are. So here we have a general overview of the sort of diagrams we're going to be creating here. They kind of look like this. We have some type of object, or indicate that by solid lines, and we have some type of image that's going to be created over here. And if it's a real image, we can trace and create light rays, and all of them will eventually go and converge to this image. Now, if it's a virtual image, instead of it all converging away, it'll actually all diverge away, and then we'll get to those. We'll get to those examples when we get to it. But we have another thing called the focal length. So that's the distance from the lens into this one special point. And we'll talk about some of the special properties here. But what's going on here? So why are the light rays bending? Well, we learned last time with Snell's law that if you have light go from one medium to another, they can actually bend. And so we can draw similar diagrams with mirrors as well. You're going to have, instead of it bending, it'll just be reflecting off a surface, and that as we change and curve that surface, it's going to be bouncing off in different directions, but ends up being really the same sort of mathematics, which is really interesting. We have something over here called the optics equation, or I don't know, sometimes I call it the lens equation, but this is the general thing we're going to use. It's true for both mirrors and lenses, as long as they're very simple. So it's saying 1 over the focal length. So this focal length, something like the distance here, it really just controls how curved the mirror or the lens is. So how strong is it effectively? That's equal to 1 over the distance to the object. So that's this distance here, goes from where we put the object to the lens. Now we have to be very careful with the signs of all these things with the focal lengths and distances. We'll talk about the conventions in a bit. And the distance to the object, which plus 1 over the distance of the object, that's the distance from the lens to this thing here. That's typically what we're going to be looking for when doing these sort of problems. We know about the lens, we know about the object. Sometimes the other ways around. As long as we know 2, we can get the third one. Okay. Another thing that will be interesting is we might be interested in the magnification. So I have a lens on this camera, we have lenses on other cameras. Well, how big does that image actually look? Because if we look at it, it may look really small, so I want some type of zoom camera that actually magnifies and makes it look bigger. So that can be calculated by the distance to the object here over the distance to the object, and then we have a negative sign. So the sign that ends up in the magnification depends whether it gets inverted or not. So if it's negative, it does get inverted. Okay. And if you want to get the height, you multiply by the magnification. Hopefully that makes sense. So we get down here, and there's a lot of sign conventions. This is something that probably shouldn't be able to take in all at once. Maybe a person can do that, but I needed to do a lot of problems. It's more of like to have a table like this ready when you're doing these sort of problems, or refer back to either this one or an equivalent one. So a few ones I think that make sense. We can talk about mirror. Mostly the things are the same, but there's some changes going from a mirror to a lens. So for the distance to the object, if it's positive, it's real and in front of the mirror. If it's negative, it's virtual and behind the mirror. Again, we'll talk about what virtual objects and images mean in a bit, especially virtual objects. That seems a little weird. Okay, for DI to be positive, it is real and in front. So this is the one difference we'll see with lenses, that if it's positive, it's actually behind the lens, because mirrors normally reflect light back at you, as opposed to lenses refracting it, just sort of switching the direction a little bit. Oh, and so for the focal length, if you have a concave, again, mirror that's curving in towards you, the focal length is positive. When if we have a convex one, it is negative. So we have to be careful when we're given a lens or a mirror. We have to make sure we get that sign right, because that can really mess up our stuff. And then for magnification, plus it's upright, it's negative, it is inverted. Now, a lot of these things are similar over here, but we notice that the not the real versus virtual, but the positions for lenses of the images gets flipped, and also what is convex and what's concave, whether it has positive or negative sign, gets flipped. A convex lens is more of a standard sort of lens that we think about focusing the light here. So this would be a convex lens here, when concave ones tend to make light diverge. So at least for objects that are far away. We'll get to it in a moment. So let's do some problems. Let's talk about first mirrors. We'll do some problems with mirrors. We'll do some problems with lenses. We'll be using a lot of the same math. A lot of these sign conventions are pretty similar, but we'll have to switch them a little bit, and we'll be able to figure out a number of things using this math, okay? Okay, so this is a problem where we're given the image, we're given how far away it is, and we're also told something that we'll get to the focal length, and we actually want to figure out where the distance to the object is. So we're told the radius of curvature of the mirror. It turns out the focal length is just that divided by 2. That's just sort of a random little fact you need to know. Focal length is 20 centimeters. Distance to the image, now we have to be very careful with this, is negative 20 centimeters. So recall that when we're looking at mirrors, we have a virtual or image that's behind the mirror. It's behind, I'm always going to draw it so that the front of the mirror is to the left. If it's behind, so the right in the case of how I draw it, it's got to have a negative sign. We have to get that right. Okay, just let's just be careful. So we write out the optics equation here, and we notice we have the focal length, we have the distance to the image. We want to get this, so we're going to solve for it. We're going to go subtract the distance of the image the other way. So we get this thing, and so we can go. We're going to need to invert that. So if we use this, we go and combine these denominators here, we'll get this equation on top. So we're multiplying this by di on each side, and f on each on top and bottom here, and I'll have the same denominators. We can just add the tops then. Okay, and then it's very easy to invert that. We just go flip that back over. If we want to get actual d0, not 1 over d0, we have both of these numbers. We have di, it's negative 20, focal length is positive 20 because it's a concave mirror. We just go put that in the math. We'll find that the image had to be 10 centimeters in front. So again, it's positive 10 centimeters. That means the object is a real object and it's in front, okay? Going back to our sign convention, okay, it's positive, it's real, and in front, okay? So if we draw an image about what's going on here, we have a object here and we have an image here. So typically we do this problem, we'll do this a few times. You draw a number of light rays. So for mirrors or lenses, it's really good to draw one that goes right to this middle point here. This, for lenses, this will always pass straight through. For mirrors, it always bounces straight off. And for here, there's going to be some line that you go up, and then it'll be parallel to this general plane here. And so we notice that the light rays really aren't converging to this one point. They're actually diverging away from the same point here. So this is not a real image. We know that's behind, it's not real, but this is what we mean by a real versus not real image, or virtual image. This is a virtual image. A real image is one that you could project onto a projector. So the light rays are all converging to one point. Here the light rays are not. Look at the light rays. They're all going away. They're never going to meet again. They're going off into infinity, but we go back and recreate this in our mind that it looks like there's an image here. So, but it's not actually where the light rays are converging. We'll get to some examples where that's true, but it's a virtual image. That's sort of what's going on. So we want to figure out the magnification. We have both of these numbers. We just found the distance to the object. We put that in our equation. We notice we get a +2. So positive for magnification means it's going to be upright, And 2 means it's going to be twice as big. So it had, maybe it's 2 centimeters high. The image is now going to be 4 centimeters high. And we can see that makes sense with the picture. I have this magnification still upright, and it's 2 times as high. So that sort of matches up in the picture and in the math. Okay, hopefully that makes sense. We'll keep going with this idea. So let's talk about the situations where you get a real versus a virtual image. So again, reinforcing, if image can be projected on a screen, the image must be real. So real images are created when light rays converge. Imaginary images or virtual images created when light rays diverge, just like the last problem. So if you have the light rays converge in something like this, you can see that's fundamentally different to this situation where instead you're sort of drawing back after. So in this problem, we're told that we have an image that's in front of a mirror, and we have an object that's also in front of a mirror. These are both greater than 0. So it turns out this has to imply that the focal length is greater than 0. So therefore, this had to have been a concave mirror. So given some information about this, we're told that the magnification is a positive 5. So we have the object, we have an image, and it's 5 times bigger, and it's still upright. That's going to give us a distinct relationship between the distance to the object and the distance to the image. Image had to have been 5 times further away, which means that the object had to have been at 1 meter if the image is at 5 meters away. So what does that tell us about the focal length? So we can actually calculate that. We use the optics equation here. We know that the distance to the object is 1/5 to the distance of the image. We plug this relationship in here to the general optics equation. 6 over di. We calculate the focal length from the distance to the object, which is 5 meters. We get that it indeed is a positive number. We, in fact, have to have a concave mirror that creates this. It turns out convex mirrors in this situation are always going to create, virtual images that go behind the mirror. But we can keep going through this. So we actually can also explicitly calculate the distance to the image. We do that 1/over thing that we figured out in the last problem to calculate the distance to the object. We know the focal length, we know the distance to the image now, plug it in, okay, it's 1 meters. Or, we could have gone up here and if we knew the distance to the image was 5 meters and, we divided by 5, that would also have solved it. But, either way, it solves these sort of things. So that's a little bit about mirrors. Let's talk about lenses. Again, it's going to be very similar. We're going to switch a couple of the sign conventions, switch things a little bit, but it's ultimately going to be very, very similar. Okay, so now we're going to talk about what happens when we have a convex lens, so no longer a mirror. Instead, now we're just bending light a little bit, creating images on the other side. So what happens if we take an object and we make it to the left of the focal point, then at the focal point, and then to the right of the focal point? How does the image change? So we're given numbers for this, but these sort of things are generally true. We're told the focal length is 10 centimeters. We're told the distance to the object is going to be 20 centimeters in this case. Again, we have the same optics equation. Nothing changed here, except some of the signs. So for instance, for a convex lens, the focal length is going to be positive. So it is a positive 10 centimeters. Okay, we go and do that inverted thing we figured out in the first problem. We have all these numbers over here. We have the distance to the object, and we have the focal length. We put those in. We'll find out the image is at 20 centimeters, and that's positive. But for the sign convention for lenses, that's behind. So we got to be very careful. This is 20 centimeters here in this direction, but that's positive. Okay, so notice that the image is real, so we go back to our sign convention originally. Sign convention for lenses, if it's positive, it's real and behind. Okay, and we can see that it had to have been real because all the light rays converged to one spot. That had to have been a real image, but it's inverted. Okay, well that's hopefully that feels comfortable. We go and can convert, that makes sense with regards to the picture. And we go look at the magnification. We put in 20 centimeters. That negative sign still stays there. So it's the same height, 1, but it's been flipped. And so let's also talk about how we can create these images for lenses. So usually, for mirrors and lenses, you can create 3 lines. One of them going through the top, that's parallel, and then going to get bent, and it's going to go through the focal length. That's what I meant, the focal point, that's a focal length away. you can create a diagonal line that goes through, and this one doesn't get bent at all. Then you draw one that goes through the focal length, then gets bent, and then is parallel. Okay, so that we're always going to follow that convention, drawing those 3 lines, one through each focal point, and then one through the middle. And we're always going to get this parallel stuff, that's sort of a special property when something goes through the focal point. Okay, what happens if you put an object at the focal point though? So let's put in the math. We can do the same inverted stuff that we did before. We've already solved for this. We notice that the distance to the object and the focal length are the same thing. They're the same distance here. So we get some number over 0. And so that's not defined, but if we take limits getting very close, we get larger and larger answers. It's essentially implying that the image is going to be infinitely far away. It's going to be whoosh, way over here. Why would we think this? Well, when we draw the lines, so we go through the one, we can't quite draw a line through the focal length here. It's kind of weird. We can draw this parallel line, the first one, then that one goes to the focal length. Okay, it's going that direction. And we draw this diagonal line. Well, notice that they're parallel. And if they're parallel, then they're going to stay parallel forever, and they're never going to cross. So it's not going to ever form a coherent image. There's lines are neither converging the same spot or diverging from the same spot. So there really isn't an image. Light rays are parallel, and the magnification is infinite. I mean, math breaks down a little bit, but you can sort of understand that kind of messes with stuff a lot, and we get this weird situation where we don't have an image because it's infinitely far away. Okay, but what happens if we take that object now and put it closer than to the focal length compared to before, where we're doing it outside, at focal length, and now inside? Well, we put in our math, same equation we've been putting in here, but this time we're going to put the distance as 5 centimeters away, which is certainly within the 10 centimeters. We do that, we find the image is negative 10 centimeters. Okay, so we can sort of see what this happens. If this number is smaller than this number, the distance to the object is smaller than the focal length, we'll get a negative sign here. And so it tells us that the distance to the image is 10 centimeters, and it's negative. So negative means it's going to be virtual, and it's going to be in front for lenses. So it's sitting here, it turns out it's at the focal length, but you could set it up so that's, over here. So this image is virtual. If we draw the lines, we'll draw a line going up, and it's going to go parallel forever. So as opposed to drawing parallel and it goes through the focal length, they won't. So you can sort of think about this line as the other side is going through the focal length. That's sort of how we, can maybe think about this. Draw one that's parallel, goes through this focal length. Okay, sure. And that one seems relatively normal, and then draw this normal diagonal line. So essentially, instead of drawing this one, we're drawing it up here like this. Because if we draw this one, it will kind of go down like that. It's kind of weird. So light rays do not converge. They're diverging. They're splitting apart as they're going. So it's not a real image. It's a virtual one, and we trace them back, and we'll find where that image appears to be. It's going to be behind, well, in front of the mirror, but it's not going to be real. No, mirror, lens. We're talking about lenses. It's going to be in front of the lens, but it's not going to be a real image. So it's not something. It's not like a normal projector lens where you can shine light through it and project it onto a screen. This is going to be in front. That's not going to work like that. We also can get the magnification. Put in these, we have these numbers now, 10 and 5, plus 2. So it's going to be upright and twice as tall, and that matches up with what the picture is telling us. Okay, so what are we looking at? So if we put it, we have a convex lens, which is really most typical ones we can think about. This is usually what we do, how we create projectors and decent number of glasses, although not all glasses, because some people are farsighted versus being nearsighted. If we want to make an image that's real, we put the object farther away than the focal length. Now, if you put it at the focal length, you get this parallel thing, and the image is infinitely far away. If you put the object in the focal length, it creates a virtual image, and on the other side, on the same side as the object is. Okay, let's do one more problem. This one's going to be a little complicated compared to the ones we're doing, because we're going to use 2 lenses. And these problems are probably the hardest things going to be asked in these sort of these sort of optic problems. And you can really solve them if you know this one trick. And the trick is that if you have more than one lens or mirror, use the image as one as the object of the other. So you do one problem, pretending there's just this one image, usually this one out front, to the left. You do the problem, where's the image? And you find an image, and then it's the object to the second lens. And then, the same thing for mirrors. If you have multiple mirrors, you can figure out how to do a problem like that. Or lens and a mirror, just feed it with the answer to one as the input of the other one. Now, you gotta be careful, and we'll do this, is we're gonna get distances in terms of this first one if we do the problem that way. But when we input to the second problem, we need to use this distance, the distance of that lens or mirror, or whatever we're gonna use. So we're told we have an object that's 4 centimeters away, this convex lens. This convex lens has a focal length of 8 centimeters. We have a concave lens of a focal length of negative 16 meters. And these things are sitting, centimeters. These things are sitting 6 centimeters away from each other. So where does the first image lie? Where does the final image lie? Okay, well, I've drew them, but we'll pretend we don't know that yet. All right. I'm going to keep track in terms of subscripts. So we want to find the distance of the first image. Again, we did that weird inverse rule. We have that all set up. We know the distance of the object, 4 centimeters. We know the focal length, 8 centimeters. So we put that all in. We find the distance to the image is 8 centimeters. Now remember, for lenses, negative means it's going to be in front and it's going to be virtual. So this is a virtual image. And that is going to be here. So it's actually directly at the focal length. It's actually really similar to the last problem we did here, where we put something halfway in between the focal length. This image is going to be sitting on the focal length of this first lens. Okay, so how do we find the final image? So now we need to input this distance to this lens. So we gotta be very careful, otherwise we're gonna get messed up. So what's the distance to that lens? We have 8 centimeters and 6 centimeters. So this distance overall is gonna be 14 centimeters. And then we have the focal length of this second lens that's negative 16 centimeters. That's a concave lens. It picks up a negative sign. Okay, we can go and put that in for all the stuff, and we get negative 7.47 centimeters. That's from the second lens. That's where this image is going to lie. Now, so this is going to be in front because it's a negative, and it's going to appear to be virtual, but we'll get to that in a moment. So one thing we'd be interested, what's the magnification created from this joint system? So that's actually going to just be the two magnifications multiplied by each other. So we do the first image and object, the second image and object, 8 centimeters 4, and put those other numbers. Overall, it's going to be positive 1.07. So it's still going to be positive. It's going to be still upright. It's only a teeny bit taller, just a teeny bit taller. So it's going to be upright, sure. And we're given that the height is 1 centimeter. So the final image has to be virtual. It's in front of this lens system. So again, we have some weird stuff going on here. We have 2 lenses, but the only way we can make a image that's in front of lenses is to maybe have it be virtual. And you can, if we drew the lines for this, they get really complicated, but we'll find that they all end up being, they'll end up converging away. If we have something over here, that's flipped and it looks good, that would be a real image. But this is not looking like one of those situations. We have something that's very clearly to the left of the system. This is going to be virtual. I think that's, I don't think I need to argue too much more about that. But that's some quick survey into lenses and mirrors and the optic equation, how you can use it to solve problems. I think this last one is pretty much the hardest thing that we can be expected to do. If we can do these sort of 2 lens or maybe a lens and a mirror situation, I think we're mostly set. So that's all I want to get to today. As always, appreciate it, you watching and following along with me. Thank you for watching. I got a lot more ideas. Hopefully they're going to be coming up, but we'll see what I have time for. But thank you for watching. Okay, bye.